For the last 4 or 6 or some amount of years, we've been teaching you all about x and y and the rectangular coordinate system, which is named that because we can form little rectangles with a width of x and a height of y to get to any single point on the rectangular plane. Even parametric equations are still rooted in this rectangular coordinate system. We just happen to also include this extra variable t to define what x and y are. What we're about to transition into is a brand new coordinate system. Dun, 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 dun. Bum, 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 bum. I would have played the real song, but I figured I'd probably get a copyright strike against me, so hopefully that was good enough for you. But for realsies, polar. What we got going on over here is the setup for a polar point and the polar coordinate system. So we have something called the polar axis, which essentially lines up with the positive x-axis. We have something that we refer to as the pole, which essentially is the origin. And then we have point P up here is defined by r comma theta, so not xy, r comma theta, where r is the radius, which is the distance from the pole, and theta is the angle from the polar axis, okay? And what's neat about this is that we can actually have a negative angle, which means we would go this way. So we would go clockwise from the polar axis. Positive angles go counterclockwise. We can actually have a radius that's negative as well. And what's really neat about that is if we have a negative radius, what it would actually do is whatever our theta value was, it actually would have us go the exact opposite direction from where the angle was telling us to go. So 180 away from it. And that's pretty neat. So here's what a polar graph typically looks like. So there's all these crazy lines going in all the different directions, and then there's these circles going around, which is a little different than our traditional XY, which is made up of a grid pattern. So what's going on is each of these circles represent a radius of, increasing by 1. So this is a radius of 1, radius of 2, 3, and so on. And then these lines in here, we have our normal 0, 90, 180, 270. And then we have 30, 45, and 60 in all the different quadrants. And occasionally you'll also have another one here at the 15 and 75 degree mark. But that's basically what the graph looks like. So let's talk about how we actually plot points. So if I have this point here, which is a radius of 2 and an angle of pi over 3. So the first thing we do is we find where pi over 3 is. So that's going to be right here. And I'm going to draw a line and extend it to the other side. Okay, so it goes all the way through. Next, we'll look at what this 2 is. So what we'll do is go in the direction of pi over 3, 2, and that's where we'll put this point. And this is the complete point right there. So we don't need the blue line, it's just the pink part. But you can put the blue line there if you want. It's useful to help you figure out what's going on. So this next one is a little weird because we now have a negative radius, which we've pretty much never allowed in math before, but polar, it's 100% cool with it. It doesn't care. So starting off again, we'll find 3 pi over 4. So that's going to be this line right here in the middle. So there we go, mark that off. And now a radius of -1. What's going to happen with that is instead of going in the direction of 3 pi over 4, so instead of going where my mouse is in the second quadrant, we'll actually go the opposite. So the point's going to end up down here, down in quadrant 4 instead. Now you might be wondering, well, hey, maybe we can actually write this as a different point then. Why aren't we saying this is the point +1 and then 7 pi over 4? And you're right, we totally can write that as another point. So that's one of the huge differences, besides all of the other ones, between polar and rectangular. Rectangular, whatever your xy is, that's your xy. That's where the point is. In polar, we actually have an infinite number of points that we could use that all could end up being the same exact point by basically just going around the circle an extra 2 pi or using negative radiuses to help us figure that out, which we'll explore in a little bit. This last one is a -45. So for a -45, we would go down to -45. So that's right here. And again, I'll extend it all the way through. And then we have a radius of 3. So now this is a positive radius. So we'll go in the direction of -45. 1, 2, 3. And there is our point. So before we move on from these, I want to just go through and show you some of the other points that we can create while using polar points. So we're going to find 4 separate ones for each one, and I've filled in the starting ones kind of in an order. You'll see once we start filling them in what the order is. But so let's look at this first one here. So this was radius of 2 and an angle of pi over 3. So what if we left the radius as 2 and then just used a negative angle to get all the way over here? And that's what we're going to do first. So what would that angle be? It would be 2, and then it would be a negative, and it would be 5 pi over 3. So 2 and positive pi over 3 and 2 and negative 5 pi over 3 both give us this same point because they both fall on the same angle, which is over here with the 2 acting in that direction. Now for these 2 down here, what we're going to do is do a negative radius for both of them. So if we're doing a negative radius, that means that we need to make sure the angle puts us in the opposite quadrant so that the negative sign will shoot us in the opposite direction, so ending up here. So we can do that by using a positive angle and a negative angle. So if we use the positive angle, that's going to be 4 pi over 3. That did not format correctly at all. Let's try that again. There we go. And if I use a negative angle, this is negative, negative 2 pi over 3. There we go. So all 4 of these points, trying to make that not be highlighted, there we go, all give us this exact same one, this same pink point right here. And they're just completely different from each other look-wise, but really they're just using a whole bunch of coterminal angles and then also using the property with negative radiuses in polar, which says that a negative radius will shoot it in the opposite direction. So I want you to pause the video right now and see if you can figure out the other 6 that we're missing for these 2 sets. And then when you unpause, I will be here ready to explain. I can't believe that you didn't actually pause and do it and that you're just sitting here watching the video. For those of you who actually did pause, that wasn't for you, just so you know. All right, let's do this first one. We're going to do positive, positive. So if I have a positive radius of 1 and I need a positive angle, then this is going to be, what is that going to be? 7 pi over 4. No idea if that's going to auto format right. Wonderful, good. Here, let's do a positive radius, but let's use a negative angle to get here. So that's going to be a negative pi over 4. And there we go. We already got this one. If I want a second negative radius, but this time a negative angle, then I need to end up in this quadrant, but using a negative angle, that's going to be 5 pi over 4, negative 5 pi over 4. There we go. Let's use positive radius and positive angle. So I'm going to have to get over here using positive angles. That's going to be 315. So I'll have 3, 315. There we go. Down here, I want to use negative radiuses for both of these ones. And this one will have a negative angle as well. So let's see, if I use negative radius, I need to be in the opposite quadrant. So I need to end up over here. So I can use positive 135 and negative 225, I believe. Just bear with me while I type that in. Boom, there we go. So all of these are just the normal ways of writing the points if we go between 0 and 2 pi. Okay, so that's going to be for these sets over here with the positive and a negative radius, and then also going from 0 to negative 2 pi, which would be what these 2 are doing over here. So if you turn to the next page, you'll see that there's a general formula that we can use to write what all of them would be. So here we have the way to find all possible polar coordinates of a point. We have 2 different ways written right now. So we have one right here, which is just when you have a positive radius, you can basically just use a positive angle and then just keep adding 2 pi to it over and over and over, where n is just some integer. Or we could use a negative radius, and then if we're using a positive angle, we have to add pi to it. So remember that that will make us go in the opposite quadrant so that the negative will push us in the correct quadrant. And there is also a fancier way of doing this, which is with this right here. It's a little bit tricky to figure out, but basically this actually takes into account both sets of these. So we have -1 raised to the nth power. So when n is odd, r will be negative, and that will give us a odd multiple of pi, which will put us in the opposite quadrant from where theta actually is. If n is even, then this will become a positive number, so we'll have a positive r, and then this will end up bringing us right back to the same place where theta is. So I just thought I'd mention that. You'll probably never use this fancy one. We'll probably stick to these two and just write it out this way. For the next two examples, we'll just look at my answer key for it. It'll be easier than me attempting to type things at the same time as talking to you. So first one, we have what are the polar coordinates for the pole? Now remember, the pole is basically the origin, so right here. So if we were in school, you would guess a couple different things, and we would basically end up settling that as long as the radius is 0, it doesn't matter what the angle is, we're always going to be right here with a radius of 0 means we don't leave the pole. So we could write the coordinates of the pole as 0, theta, where theta is any number in the world in either degrees or radians. It doesn't really matter. For part 2, it says find all polar coordinates of this point, 3 pi over 3. So here I've graphed it for us already. This is the same one that we've already done in the first polar one that we graphed. And kind of the easiest way is to find the 4 different versions of the point. So positive, 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 negative, negative, positive, and negative, negative. And then just for the angle, add 2 pi k, where k is any integer. So you don't need to list all 4 of these ones out. There are shortcuts that you could use following the stuff up in the notes right above this part where you can't actually see because I can't scroll where I am right now. Or you could use the super fancy way if you wanted to. Any of those would work. This is just the simplistic way of doing it. You just list the 4 major points between 0 and 2 pi and 0 and negative 2 pi with the positive and negative radiuses, and just add a 2 pi k at the end. Boom, done. So let's try to figure out how these two things relate to each other a little bit more. So what I'm going to do is overlay the rectangular coordinate system on top of our polar one. Okay, so now this will also be the point x, y, and that means that this distance right here is y, and this distance right here is x. I'm hoping you're starting to see the connection that we just created here, which is a wonderful right triangle with a side length of x, y, and r. So we can use the relationship between right triangles with Pythagorean theorem as well as trig to help us relate r and theta back to x and y. So let's start off with if we want to switch, let's see, from r theta back into xy. Okay, so that means we were given r and theta and we want to end up with x and y. So let's think about this. In this triangle, is there anything that relates r, theta, and x? And I'm hoping you already know it because we've been doing it for a while now, but cosine theta is equal to x over r, and if I just multiply r to the other side, I'll get that x equals r cosine theta. And hey, we already knew that from vectors, right? We would have magnitude cosine theta in vectors, and the magnitude just so happened to be the distance between the origin and where the vector stopped. So this is essentially the same as vectors. And we can do the exact same thing for the y value. It's going to be y over r is what sine equals. So then y is going to equal r sine theta. So if you're given r's and thetas, we can find what x and y is by just doing r cosine theta and r sine theta, just like vectors. Okay, so I'm hoping you are able to make that connection nice and strong. This is the exact same thing as vectors for this first part. Now let's say that we are given x and y and we want to switch it back to r's and thetas. Well, just like in vectors, if we wanted to find the magnitude, which is the same as a radius in polar, we would just say, okay, well, x squared plus y squared, that's going to equal r squared, right? And that was the magnitude. I mean, we always would write it as magnitude equals the square root of a squared plus b squared, but it's the same exact formula. And then in this, if we want to find theta, well, that's going to be tangent of theta equals y over x. And then we would normally, write it as tan inverse of y over x, but that's going to be pretty easier to remember, this one, I think. So we now have a way of switching back and forth between polar to rectangular by doing x equals r cosine theta or y equals r sine theta, And we can go from rectangular back to polar by using x squared plus y squared equals r squared to find the radius, and doing tan inverse of y over x to help us find theta. Now remember that that will give us a reference angle, and we might need to change that up a little bit. So for 3a, we are given polar coordinates. So remember that means this is r and theta, r and theta, r and theta. And we're being asked to find the rectangular coordinates, which is x and y. So we can just use our conversion over here to say, okay, the x equation is going to be r cosine theta. So in this case, that's 3 cosine 5 pi over 6. And the y will be 3 sine 5 pi over 6. So this isn't good enough. We need to just keep going if we can simplify it. So we need to figure out what is cosine of 5 pi over 6. So let's see, 5 pi over 6 is a 30 in the second quadrant. So cosine of a 30 is the square root of 3 over 2. It is negative because we're in quadrant 2, so this is going to be 3 times a negative square root of 3 over 2. And then sine of a 30 is going to be 1/2, and it's positive in that quadrant. So we have 3 times 1/2. That's our point here. So if we just kind of simplify this, we have negative 3 rad 3 over 2, comma, 3 over 2. So this is point P in XY form. Part B is going to be the exact same thing. So I'm going to just do it down here because I have a little bit more space. So I'm going to get 2 cosine negative 200 degrees and 2 sine negative 200 degrees. And I'm just going to type these into the calculator. So cosine times blah, 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 negative 1.88 and 0.68. Now it's really important that you remember that you need to be in degree mode because we're using 200 degrees. Your calculator was probably in radians, so you might want to switch that out. But there you have it. It's very straightforward. I hope you're making the connection between vectors with the magnitude and direction angle because they are 100% the same exact thing. For 4a and b, we're being asked to find a single polar coordinate. 'Cause remember that there's a lot of these things because we can pick different angles or different radiuses with a different angle to help us get to the same point, just like we did earlier. So we're just going to pick normal one. And normally, in this particular situation, what we do is we always try to find the positive radius and the positive angle if we're being asked to find a single one, unless it's just way easier to do like a negative angle or potentially negative radiuses. Negative radiuses tend to be a little bit on the harder side. But so here they gave us an x and a y, and I actually think the easiest thing to do is to just quickly sketch where this is. So we have -1 and +1, so that's going to be right here, and I'll just draw a little triangle off of this. So doing that allows me to figure out really quickly that that's a 45 and that this is going to be the square root of 2. So I actually know everything I need to know about this. The radius is going to be square root of 2, so r of the point is going to be square root of 2. Now I need the angle. So I need this angle. So if that's 45, then the angle can be 135. And I'm done. This is in r and theta. Same idea with 4b. I'm just going to draw it real quick. So I find this -3, 0. It is right over here. So let's think about what angle this would be. So I think it's easiest to say that that's 180 degrees, and then we would have a radius of 3. Okay, so our polar point is going to be 3, 180 degrees. Now, just as a sidebar, let's talk about something else that we could do here, which is kind of interesting. Let's say that we had an angle of 0 for this one. Then we could use a negative radius to put it over here. So this is in r and theta, and this one up here was x and y, and we actually have something that looks really, really similar. So either one of these ones work. I mean, there's a whole infinite number of ones that we could do. For 5, they're asking us to convert this polar equation. Okay, so now it's an equation because we have an equal sign, it's no longer points. Polar equation into rectangular equations. So rectangular equations can only have x and y, no other variables. So we're going to be using this information over here to help us figure out how to do that. So the first thing I notice is right here with this cosine. If that happened to have been an r cosine, I could just immediately replace it with x. So what if I just multiplied both sides by r? So I'm going to sneak it in right there, and when I do r times r, I'll get r squared. So right now I have r squared equals 4r cosine theta, and r cosine theta is x. So I can rewrite this side as 4 x, because these are identical to each other based on our conversion. And then we have r squared. Well, r squared is really x squared plus y squared, so we can just come over here and replace this side with x squared plus y squared, because that is identical to it. And in theory, we're done because we have a rectangular equation, but they've asked us to identify it, and there is a little bit of space for us to graph it. So let's actually put this into the standard form of what's going on with it. So I see two things that are added. This is most likely going to be an ellipse or a circle. So let's go about doing that. I'm going to subtract the 4x over. I'm going to need to complete the square here. So I'm going to do plus space there. I got my plus y squared equals, and then a plus space to line up with this one. Remember, the trick is to take the middle term and divide it in half and square it. So that's going to go right here. So I'm going to have plus 4 plus 4. The secondary trick here is whatever this inside is what's going to be right here. So that's going to be an x minus 2 squared plus our y squared equals 4. So I can tell that this is a circle. I forgot how to spell. A circle with a, let's see, a radius of 2. And it has a center at 2, 0. And one of the things that we're going to be working towards as we continue into graphing stuff is to be able to look at this equation and recognize it right away, what it is. So if I just did a super rough sketch of this particular circle, it's going to be right here, center at 2, 0. It touches the origin and it goes away from that. And if we look at this equation right here, r equals 4 cosine, so that 4, that actually is helping us figure out the radius or the diameter in this case, because we're going 4 out is what this would end up doing. And cosine, which is related to x. And look at this circle wraps itself around the x-axis. So ultimately, we'll be able to look at this r equals 4 cosine theta and be able to draw this rectangular graph. No problem, super easy, super quick. And then we can say what its equation is just because we recognize it from polar. For 6, we just have another one, convert r equals 4 secant theta into rectangular, and then identify the graph. So what I'm going to do here is, I don't have anything that deals with secant, but I do have stuff that deals with cosine. So I'm just going to rewrite this as 4 over cosine. Remember, secant is 1 over cosine. And I don't have anything with denominators either, so let me multiply this cosine to the other side. I'll end up with r times cosine theta equals 4. R cosine theta is x, so this is really x equals 4. So this is going to be a vertical line. If I were to just do a quick sketch of it, right, 1, 2, 3, 4, it's going to be right there. And eventually, we might be able to start recognizing that if you have something like 4 secant, that's going to end up being a vertical line. And if maybe we had something like 4 cosecant, that might end up being a horizontal line. Now we're being asked to go the other way for number 7. We're given a rectangular equation and we want to convert this into polar. So we could just immediately replace the x and the y with r cosine theta, r sine theta, but that's going to get really messy when we try to simplify it and we end up having to try to FOIL those things out. So it's actually much easier to just FOIL it out in rectangular mode before we switch it to polar. So I'm just going to do that. This will be x squared minus 6x plus 9. This one will be y squared minus 4y plus 4 equals 13. And then I'm just going to group the squared terms together. So x squared plus y squared. Group the single x and the singleton y's together. I have a 9 plus 4, that's 13. It will end up canceling out with the 13 on the other side. And now I can start replacing things. So this x squared plus y squared, we know that it's r squared. A 6x, x is really going to become r cosine theta. And a 4y, the y will become r sine theta. And I noticed a couple things about this. All of these have an r, so I can just divide everything by r. And then in order to get rid of these negative signs, why don't I just move them to the other side by adding them? So I'll get 6 cosine theta plus 4r sine theta. So if we're thinking about what this graph is up here, right, it's a circle that has a center at 3, 2, and then a radius of the square root of 13. And we can see bits and pieces of that happening over here. So we have this 6, well, in the x direction, we had the center was at 3. And in the y direction, it went up 2, right? That was what our center was. So those are connected by just cutting those in half. And I know that the 3 went in the x direction because cosine's x, and the 2 went in the y because sine is y. And from there, it gets a little bit harder to figure out where the 13 comes from. But, I mean, we could do the math right here to try to figure that out. 3 squared plus 2 squared is going to end up giving us that 13 that we need. So for example 8, we have a radar detects 2 airplanes at the same altitude. Their polar coordinates are 8, 110, and 5, 15. And we want to figure out how far apart they are. So let's just label some things on our graph real quick. So here, this one goes out 8, and this one goes out 5. And what we're trying to find is the distance between them. So this line right here, that's the distance we're trying to do. Now let's look in here. If we want to figure out how far apart they are, well, we can just subtract, right? So we have 110 degrees minus 15, and that's going to be the angle in between. So there's a couple different ways that we could go about solving this now. So we could just use law of cosines. That might be the way that I would probably do it. And we would have just, x squared equals 5 squared plus 8 squared minus 2 times 5 times 8 cosine of 95, kind of cutting off over there, my bad. And then just, this is all calculator work from here, so we would do x is going to be 9.797 miles. And that wasn't too crazy difficult. We just converted it back to something that we learned a long time ago, and it made our life really, really easy. We could also do this with vectors if we really wanted to. I don't necessarily think you should, probably. I think it's a little bit harder, but we could figure out that the vector of one of these planes, right, are cosine theta, or magnitude cosine theta, magnitude sine theta. We can say 8 cosine 110, and then 8 sine 110. Those are in degrees. And then the other one is going to be at, 5 and 15. So that's going to be 5 cosine 15 and 5 sine 15. And I know it's been a while since we've done vectors, but we can actually find what this is by just subtracting these two vectors from each other. So if I did that, I would get that the vector that's the subtraction between these two things is going to be negative 7.56 and 6.22. And if I just find the magnitude of that, that's going to end up being 9.797 miles. So that was it in vectors. We could also convert this to rectangular mode. So this is essentially what I wrote in vectors. It's the same thing to convert this into xy. So I would just do 8 cosine 110, 8 sine 110. That gives me the xy here, and then I could literally just do the distance formula to find the distance between the 2 points. So lots of different ways of doing this. My suggestion is just law of cosines. It's the fastest and the easiest. For question 9, we have a similar setup, this time with 2 ships instead of planes. We have the first one is at 3 miles and 170. So here's approximately 170. There is the 3 miles out, 1, 2, 3. And next we have 5 miles and 150. So here's 150 and 5 out. There's our 5. We want to find the distance between the 2 ships. So we're looking for the distance right here. And then you can see I already labeled in that the angle in between these 2 ships is 20 degrees. So now that we have this particular setup, it's just normal triangle. We can use law of cosines, we could use vectors, we could actually convert these polar points to rectangular and solve away. I'm just going to use the law of cosines for this one. And let's see, so that's going to be x squared equals 3 squared plus 5 squared minus 2 times 3 times 5 cosine 20 degrees, the angle in between them. And this is just straight calculator work now. Just plug it in and add the units, and I'm done. We can do the same thing with vectors. I show that in the answer key if you want to look at that. And again, you could convert this back into xy and just do the traditional distance formula. That is the longest and hardest way possible though, so not recommended.